Okay, a couple of videos ago, I showed you how to determine whether a particular collection, a given collection of vectors, formed a basis. But what if you're looking for a basis and you don't have a set of vectors to start with? Apart from the standard basis, how could we figure out what a basis of a subspace is? Remember that by definition, a basis spans the space that it's in and is linearly independent. For any particular set of vectors, there are four possible combinations of spanning and linear independence. And those are, let's do a chart here. We'll talk about independence and span. It's possible that the set of vectors is independent and spans the space. It's also possible that the set of vectors is independent but does not span the space. Equally, it's possible that the set of vectors is not independent, but does span the space, and that it is not independent and does not span the space. In the first case, we have what we call a basis, right? If the set of vectors is both independent and spans the space, we call this a basis. The set of vectors we're talking about that meets these criteria is what we call a basis. That's the definition of a basis. If the collection is independent but does not span the space, then there aren't enough vectors in the collection. The vectors that are there can be linearly independent, but there aren't enough of them to span the space. In this next case, we have vectors that span the space, but the vectors are not linearly independent. That means that there are enough vectors to span the space, but some of them are linear combinations of the others, and so there are too many vectors in the collection, in the set. The last instance is kind of trivial, but I'll give you a quick example. If the vectors in a collection they don't span the space, then that means, for example, I don't have enough vectors in the collection. Let's use vectors. I'll use 1, 0, 0, 0, and 2, 0, 0, 0. So what I have here is two vectors, but they're in R4. So there aren't enough vectors here to span the space. I would need 4 vectors to span R4. Equally, these two vectors, the two vectors that I do have, are not linearly independent, right? One is a scalar multiple of the other. So these two vectors are neither independent nor do they span the space. So in the first case, well, let's skip the first case for just for the moment. In the second case, I have not enough vectors. In the third case, I have too many vectors. In the fourth case, I kind of have both because I have not enough vectors. And the ones I do have are redundant. So to all intents and purposes here, I don't have 2 vectors, I only have 1. Okay, but that's the linear dependence aspect. In the first case, knowing that the vectors that I do have span the space tells me that I have enough vectors, right? I have at least as many vectors as I do dimensions. Knowing that my vectors are linearly independent tells me that I don't have too many. I don't have any redundancy. So here I have just enough vectors to span the space and no more. Okay, so let's take a look then at how to tell if a collection of vectors forms a basis. I'll start that on the next screen. Back in section 4.3, when we were talking about linear independence and dependence, there was a participation activity, 4.3.2, about minimal spanning set. In that animation, they showed you 3 vectors, but because those 3 vectors were all on the xy plane, on the x1, x2 plane, they spanned the space of R2, but the vectors were in R3. So these R3 vectors spanned a space, but they didn't span all of R3, they only spanned R2. Because the vectors were vectors from R3, they had the capacity to span, the 3 of them together have the capacity to span R3. But because they were all on the same plane, they were coplanar vectors, they only spanned R2. If you're not quite following, I would encourage you to go back to section 4.3 and the subsection called linear dependence and span, and take a look at that participation activity just to remind yourself what it was like. The fact that we had three vectors all from R3, but that the span of those three vectors was R2 is significant in what we're going to be looking at next here. What happens is you end up with more vectors than you need to span the space that they span. The three vectors together did span R2, but you don't need three vectors to span R2. You only need two vectors. And so we removed one, and the remaining two vectors still spanned R2. We called those two vectors, that collection of two vectors, the minimal or A, minimal spanning set. That's not necessarily the only vector we might have removed. And this minimally spanning set still manages to span the space that the three together spanned, but we don't need all three. One of the things pointed out in that animation is that one of those vectors was a linear combination of the other two. By removing one of them, we've reduced the spanning set to two vectors that are linearly independent. So we have two, in this case, linearly independent vectors that span the space of R2, not R3, but R2. They do span a space, and they're linearly independent. So those two vectors then form a basis for the space of R2. And that's essentially what we're going to be doing now with this finding a basis for a subspace defined by the span of a set. That's exactly what we're doing. Remember that a basis has these two properties. The vectors in the basis span the space, or in this case, a subspace. Let me just pop that in there because that's important. Span a subspace, and they are linearly independent. Those are the two requirements for a collection of vectors if we're going to get away with calling that collection a basis. Well, that's essentially what we were calling a minimal spanning set back in section 4.3. And the way we went about finding that minimal spanning set, if I gave you a set of vectors, was to put those vectors into a column matrix, a matrix where each vector was a column in the matrix, and row reduce it to reduced echelon form. And then all we had to do was identify the pivot columns and go back to the original matrix or the original vectors to determine which columns or which vectors were associated with those pivot columns. In other words, the pivot columns in the reduced matrix correspond to the vectors that make up a basis. It's not a unique collection. If you put the vectors in a different order, you could get a different basis, but it would give you a basis. And that's exactly what we're going to do in this section as well. We can formalize this with the theorem. If a set of vectors, we'll call it S, if a set of vectors S spans a subspace, we'll call that W. That's like our collection of three vectors in R3 in the previous example, spanning the subspace R2. Right? It doesn't span all of R3, it spans a subspace of that. Those vectors span a subspace. If that's the case, if we can find a set of vectors that spans a subspace, then this theorem tells us that we can find a basis among those vectors. We can find enough vectors from the set of S, of all the vectors, that will still span the subspace, but they'll be linearly independent. In other words, we won't have any redundancy. We won't have too many vectors. If all you care about is spanning the space, then you can use as many vectors as you want. But in order to determine a basis, we need to reduce the number of vectors to the minimum number that we need that's still spanning the set. So here's that theorem again. The basis reduction theorem says, take a set of vectors that spans a subspace. I can find a basis from some of the vectors in S, possibly all, some if not all the vectors in S. Depending on the situation, I may need all the vectors in S, but as in the previous example, I might not. I might be able to get away with a subset of those vectors. Okay, I'm going to do an example here, but before I get started on that, I want to remind you of one other thing. I'm not going to worry about the formal language in this one, but I do want to remind you about Theorem 4.2.2, the title of the theorem is that the span of a subset of Rn forms a subspace. And the reason it's important is that this subspace here that I'm talking about is the same as the subspace here. And the reason this is important is because the subspace I'm about to use is the subspace formed by a span. The span of a subset of Rn forms a subspace. So I'm going to be talking about the span of a collection of vectors, and I'll write those vectors out. I'm going to do this on the next screen because I won't have enough room here. But that span, the span of a collection of vectors, is a subspace, right? Just like that participation activity I started this video with, the span of a collection of vectors in R3, in that case, was a subspace. It was actually R2. So that's what I'm talking about when I say the span of a subset forms a subspace. And that's exactly what I'm using when I say that this set of vectors spans a subspace, W. I'm going to look for a basis, okay? So on the next screen, I'm going to write out the list of vectors. I'm going to show you the span of that list of vectors, and then I'm going to show you how to find a basis for that subspace. Let's take a look at several scenarios. This just happens to be the first one on my list. Does this collection of vectors form a basis? First of all, what dimension are we in here? We're in R3, which I can tell because there are 3 components in my vectors. If I had 3 components in some vectors and more than 3 components or fewer than 3 components in others, then I wouldn't even be able to have this conversation at all. But since the number of vectors I have here, I have 3 vectors, matches the dimension, I'm in R3, there is at least a possibility that this collection is a basis for R3. That's the first thing to check, but once I've decided that it's at least possible, then the next thing I need to do is check for linear independence. So I'm going to create my matrix. This is an augmented matrix with a 0 column. And my goal for linear independence is to determine whether or not there's more than the trivial solution or only the trivial solution. I want there only to be the trivial solution, because if there's more than that, then my vectors are linearly dependent and I'm done, right? There's no basis here. So I'm just going to do this on the calculator. I'll go away and put this into the matrix function in my calculator, and I'll come back when I have a reduced echelon form of the matrix. Well, here's my result. And I've got a reduced echelon form. I still have a 0 column here. So that means that this matrix, the system that gave me this matrix, has only the trivial solution. Therefore, this collection of vectors right here is linearly independent. That's one criteria for being a basis, but the other one is whether it spans the set or not. And that's easy to check too, because I've already done all of this work. If I just ignore, let's see, how do I want to do this? If I ignore this column, the elementary row operations that took me from this matrix to this matrix would give me the same first 3 columns, the same elementary row operations. And when I do that, I get no 0 rows here. So that means that the collection of vectors also spans R3. And these 2 criteria together tell me that these 3 vectors, if I call this collection of vectors S, then I can say that S is a basis for R3. Here's another collection of vectors in R3. This time there are only 2 of them. Therefore, these 2 vectors do not span R3. If they don't span R3, I don't have a basis. That's all I have to do here. I have to meet the criteria that the vectors are linearly independent and that they span the space. In this case, they span R3. In order to be a basis, this collection of vectors has to meet both of those criteria. If I can tell right away that they don't meet one of the criteria, there's no point in testing for the other one, because I already know that I don't have a basis here. I don't have a basis in R3. All right, here's another collection of 3 vectors, and we're in R3. And at first glance, it kind of looks like I've got the standard unit vectors here. I've got the standard basis, but I don't. This vector here is all zeros. And in fact, if I turn this into a matrix, I don't really need to do this, but I'm just going to do it anyway. I get this. And it's not really, I'm not interested in this vector as much as I'm interested in this row once it's in matrix form. I can just look at the third component in each of my vectors to see that's what's going to be that row. What I have here is a 0 row. And if I have a 0 row, then my vectors are not linearly independent. If my vectors aren't linearly independent, then I don't have a basis. I have not met that criteria, so I don't have a basis. I suppose I could have written up here, T does not span R3. So I have, so far I have a basis here. This collection of vectors S is a basis, but T is not a basis and R is not a basis. I'd like to look at just one more example, and I'm out of space on this screen, so I'll go to the next slide. Okay, so here's the collection of vectors that I'm going to be playing with for this example. I have 6 vectors in this collection, in this set, but I'm in R4. So the maximum number of vectors I need to span R4 is 4 vectors. So I know I can reduce this set of vectors. If I'm looking for a basis, I know I can reduce this set of vectors to at most 4. But those 4 vectors, or these 6 vectors, may not span R4. Remember the example I gave at the beginning of this video, the 3 vectors that we had, although they were in R3, it turned out they did not span R3, they only spanned R2. So it's also the case, it's also a possibility that these 6 vectors only span R2 or R3. So what we're going to do now is we're going to form a subspace from these vectors by taking the span of them, the span of these vectors, and this is what your book is calling W. The collection of vectors itself is what it calls S, and W is the span of S. But the span of a collection of vectors is a subspace. Like the span of the R3 vectors in the first example was the subspace R2, the span of this collection of vectors might be R2 or R3. It could be as much as R4, but that's as high as it goes. So I know I'm going to be able to reduce this some. And the way that we went about doing that when we were looking for a minimal spanning set was to set up a matrix where each column of the matrix was one of the vectors in its column form. So I'm going to have this matrix. And I'm going to, I'll just use my calculator to do this. I'll row reduce this until it's in reduced echelon form. And the result will tell me which of the matrices in the original collection form a basis. And then from that, we'll be able to say form a basis of what. So I'll turn off the recording for the moment and work through this matrix reduction on my calculator, and I'll come back with the result. Okay, so there is my reduced echelon form of my matrix. And when I look at this now, I see that this column here is a pivot column, and this column is a pivot column, and this 5th column is a pivot column, and that's it. So I can look back at my original vectors and select the same columns 1, 2, and 5, and the vectors in that collection, that's 1, 2, -1, 1, 1, 3, -1, 1, and 1, 3, 0, 1. Those 3 vectors are a basis. And because there are only 3 of them, they are a basis not for R4, which they might have been, right? If we'd done this and found there were 4 pivot columns here, we would have selected the corresponding 4 vectors, and we would have said, well, then that they span R4 because there's 4 components in each vector, so there's potential, there's capacity for them to span R4, but we only came up with 3. So this is a basis for R3. This whole span here, this whole collection spans R3, but this is the number of vectors that we need to demonstrate that. We don't need all 6 of them. So if you have a span, if you have a collection of vectors that you know spans a space, but there are too many vectors in that collection, in that set of vectors, this is how you can reduce the number of vectors in the set to form a basis. So you only have exactly enough vectors to span the subspace, and those vectors are linearly independent. What happens, though, if you don't have enough vectors? This theorem, Theorem 4.4.3, the basis extension theorem, tells us that if we don't have enough vectors to form a basis for R3, for example, if we have a few, if we have some, if we have k vectors, but we're in Rn and k is less than n, then we can extend this linearly independent set of vectors so that there are enough vectors to span Rn. So in our first example in this video, I showed you 3 vectors, or I reminded you about an exercise that had 3 vectors. They only spanned R2. Now, when we reduced the number of vectors in that set, we only had 2 vectors, but they still only spanned R2. The vectors came from R3, though, and what this theorem says is that if I have a linearly independent set of 2 vectors from a space R3, then I can extend that set of 2 vectors to form a basis for R3. So I can find a third vector, in other words. For this example, though, I'm going to use the same vectors as we used in the previous example. There were 6 vectors in Rn, and we reduced those vectors to a subset of vectors, a set of vectors that spanned a subspace, and those vectors were 1, 2, negative 1, 1, 1, 3, negative 1, 1, and 1, 3, 0, 1. And we said these 3 vectors, although they're in R4, spanned R3. Actually, I'm going to erase that last bracket there. I'm going to try to conserve space here. I'm going to try to come up with a 4th vector so that once I've added this 4th vector, this collection of vectors spans R4. And here's how I'm going to do that. I'll start by creating a matrix with the 3 vectors that I have here that were I determined formed a basis of R3. And because they form a basis, they are linearly independent and they span the space, they span R3. And then I'm going to augment this matrix with the identity matrix, essentially. So I'll have additional columns. There are 4 positions, so there are 4 new columns in my matrix. And then I'm going to reduce this matrix to reduced echelon form. Again, I'll just do it on my calculator. And when I come back, I'll have a reduced echelon form of this matrix, and I'll show you how to use that information to determine the extra matrix that we need to finish the set here so that we're spanning R4 instead of, so we have a basis for R4 instead of just R3. Okay, here's the result of that reduction. This massive matrix here row reduces to this one here. Now, if I go about selecting the pivot columns in this matrix, very similar to what I did in the previous example where I was reducing the number of vectors, I find that the first 4 columns are pivot columns. And so I'm going to go back to my original matrix and highlight the first 4 columns there. And you'll notice that the first 4 columns there correspond to the first 3 vectors. And the 4th vector, the 4th column, then is this new vector, 1, 0, 0, 0. So now I have a basis for R4 using this subset of vectors that I found. This subset of vectors spanned R3, but this collection of 4 vectors now spans R4 with the addition of this new vector. And the new vector that I ended up using was just the 4th one in the original matrix, because the first 3 columns in the original matrix were already in my collection of vectors. It should be obvious that there's no way to to further this, there's no way to add a fifth vector so that I can span R5 because these vectors are only in R4. So the most vectors you can ever come up with doing this, using this process, is the number of vectors will match the number of components in each vector. So I can only use this to expand the basis up to R4.